Good morning, everyone. Thank you for coming. My name is Jeff Williams, and I'm the CTO and founder of a company called Contrast Security, and I encourage you to stop by and check out our stuff. Today, I'm going to be talking about, some of you may have run into me before. I was very, very involved with OWASP for a long time, like from the beginning. So some of you may have seen some of my stuff. I wrote the OWASP Top 10 and WebGoat and ISAPI and a bunch of the other projects at OWASP. Today I'm going to talk about why I suspect that software assurance tools don't work on APIs. And by APIs, I'm having a broad definition here of web services, REST services, microservices, APIs, the API economy, WebSocket. Like, there's a lot of stuff in this bucket. But just in general, I think that there's some real significant differences between the traditional web application and web services that can make it very difficult for tools. So that's sort of my hypothesis going in, and I've done some research, so I've got some data at the end that we'll actually talk about. So, but I got to take a long time to get there because it's not that much data, so I can't do it in the first 5 minutes or we'd be done. So when I say do they work on APIs, I've really got a pretty specific definition of work that I'm trying to get to. So first thing is it's got to work at scale. And in fact, I encourage you, when you think about application security, to throw out anything that doesn't work at scale. Because I see all these organizations that have AppSec programs that don't work at scale. They're only doing a tiny percentage of their company's application portfolio, which is a disaster. And to work at scale means that you probably can't have AppSec experts involved with the critical path of that project, because most organizations don't have enough of you guys in order to do that work. Okay, so if you want to do if you've got 1,000 apps in your portfolio or even 100 apps in your portfolio, you can't have AppSec experts involved with every step of that because it won't scale. And that means that your tools have to be super accurate. If they're not accurate, you have to have experts to go in and weed out the false positives. And so you instantly have experts involved. So now you don't scale. In my mind, these tools have to run continuously. APIs in particular are likely to be built by Agile and Devops teams that are iterating very quickly. They need instant feedback on the code that they're writing. So I believe we need to reimagine application security tools as what I call sensors, much more like a New Relic for performance monitoring. We need our security tools to work that way, continuously running, not periodic scans, but actually continuously monitoring things. And there's a couple talks that I've done out there if you're more interested in that. And most importantly, I think we need to do a much better job of matching up the tools that we have to the things that they're good at. Because you can't just run one tool on your app and expect it to find all different classes of things. So I think we need to be much more specific about matching up, hey, this tool is really good at data flow analysis, and this tool is really good at SSL, and match up the tools to the things that we're trying to prove about our applications when we do a pen test or a code review or some kind of analysis. Right now, I see a lot of folks sort of running the tool and then trusting that the tool is going to find everything. And what I've discovered is that the tools are really not, they don't find what you expect. And this is after working in this field for 15 years. The tools, still, I didn't know what the tools actually do. And so the only way to figure out what tools do is to use some kind of benchmark. And at the end, I'm going to talk about the OWASP benchmark project, which is actually measuring what these tools are good at and what they're weak at. And then you can do this process much more intelligently. But until this project, there's no way to know. All right, so let's talk a little bit about services. API economy is really important. In AppSec USA, Alex Stamos gave a great talk. He's a CISO of Facebook and formerly CISO of Yahoo. He gave a great talk and he said, Uber's just some code written on top of 3 APIs. It's Google Maps, Twilio for notifications, and PayPal for payments. And they're $1 billion company. So this is really important. And if you look at Uber, their code is actually implemented with an API. So you can go invoke the Uber API, and they've got clients written for that, like a web client, and they've got mobile clients that probably have used. And I sort of fear the day when somebody at PayPal writes into their API some call to Uber, and then we get this feedback, and pretty soon Skynet. But that is not the problem that I'm here to talk to you about today. Today, I want to point out, like, all the same kinds of vulnerabilities that you have in web applications, almost all of them, exist in web services. So you can have SQL injection. In fact, 10 years ago, maybe a little more than that, I wrote a lesson into WebGoat that has a SQL injection behind a SOAP web service that some of you may have played around with. It's very possible to have those kinds of vulnerabilities in a web service, but you know how developers don't always validate hidden fields very well? Because they're hidden, right? Like they're not, it doesn't seem like something that an attacker could modify. Well, the same kind of thing happens with APIs. So I'm saying APIs are the new hidden field here, because it doesn't seem like an attacker could get inside your client that you just wrote and modify the fields that are being sent to the service. So developers might not think about being attacked through the API, which means they leave out things like authentication and access control and input validation and all the kinds of things that we've gotten kind of used to in the web app world. We got to go back and make sure we do them in the web service world. From the threat model perspective, I think it is a little different. I'd love to do this, a different talk, sort of build the threat model for this. We don't have time to do that today. But I will say it's a little bit different. With APIs, frequently the business data, the important assets, are very close to the external perimeter. They're not buried in some 3-tier architecture deep in a data center. They're taking that data and they're moving it right out to the edge of the enterprise and making it accessible. So when you do your pen tests and your code reviews, really think about the threat model and how this can affect the business. But like I said, we don't have time to do all that today. We need tools to solve the scale problem. Right? There's no way that we can do application security without automation. It's critical. But a couple things. So the first is that the APIs sort of exacerbate the scale problem, because now every application, instead of just having a browser interface to one web app, now you've got multiple interfaces. Right? You've got mobile clients. You might have a desktop app, you might have a browser, JavaScript app, and you might have external third parties all calling your API. So now you've got a bunch of code that you've got to manage. So now instead of just sort of one of these boxes, now you've got multiple ones. This is sort of a side note, but everybody here heard of deperimeterization? Everyone here believe the perimeter's dead? And stop calling them internal and external applications. Because if there's no perimeter, there's no internal and there's no external. We can't do that anymore, right? And if your whole AppSec program is set up around the concept of only testing the external facing applications, you've got a problem, because there ain't no perimeter, which means there ain't no internal and external anymore. So this is what I see in a lot of organizations. I see a beautiful SDLC. Anybody got one? They're pretty. They've got all kinds of great activities in them, like threat modeling and architecture review and maybe some security requirements. And a little later, you might have some training for developers and some code review, and maybe later some pen testing or scanning or something, and maybe even a check right before the application goes into production. Problem is, if any of those activities require your application security experts, you've got a bottleneck in your process. And this process is going to work real well for 1 or 2 projects, but if you try to do this at scale and run multiple projects through that process at the same time, your AppSec guys are going to get overloaded immediately. So what do? Well, the first thing is we start limiting down the number of applications that these guys have to look at, right? So we say, well, we're only going to look at the critical apps. Anybody doing this? Getting some nodding heads. So that happens right away. This is really a big problem. Then what happens is, even though just the criticals are too much, so we start saying, well, what we're going to do is we're just going to run the tools, and the AppSec experts are going to filter out the false positives, and we'll just deal with that low-hanging fruit. which means essentially you're missing anything that tools can't find. So this is really a weak process in my mind. We end up with low assurance, pretty low coverage over our portfolio, and actually we end up pissing everybody off because now we're this bottleneck that's slowing down the process for everyone, right? So I want to try and get out of this mode. And I think the path forward there is to use these tools differently, to use them as sensors that run continuously throughout the process, and use them for what they're good for. So let's talk a little bit more about that. I want to talk about some of the things that are different about APIs. And I'm going to kind of go through this stack of things. The biggest change with APIs is that they're built on top of frameworks. And they're really complicated frameworks. Like web apps are pretty simple. There's still a lot of applications that they're just servlets or just simple APIs that take a request and a response. APIs build on top of frameworks that do a lot of different things. And I'm going to go through some of the differences here. It seems like these APIs are simpler. Like if you look at the code, they could be 5 lines of code to launch a web service in some framework like JAX-RS or something. It's really actually kind of elegant. But when you look underneath, it's a ton of stuff. And it's all that stuff that makes it hard to automate the security. So let's dig in. I'm going to talk about the different levels of this. And then the goal is to identify where's the best sensor for any one of the things that we want to establish about our application. So if we want to test SSL, what sensor are we going to put in place to verify that we're doing SSL right? And if we want to know that we don't have SQL injection, where's the best place to put a sensor to detect that? So you got some options. On the client side of things, you can do traditional pen testing. You can do dynamic scanning. Or you can use something like JavaSnoop. Anybody used JavaSnoop before? Cool. It's an interesting little tool, right? Basically what it does is it infiltrates the client and allows you to hook method calls while the client is running. So instead of having to be, the next thing here is a proxy. Instead of having to be a proxy and trying to intercept the traffic, which is often impossible with rich clients and web services, with JavaSnoop you can hook it directly into the client itself and change values and then sort of do your pen tests that way. And then on the API side of things, you could use code review. I'm a big fan of that, although it doesn't scale really well. I've done a ton of code review. Static analysis, or you can use instrumentation, IAST. And I want to spend just a couple of minutes on IAST, one because I've spent the last 5 or 6 years of my life building out this technology, but also because it's kind of new. And I thought it'd be useful to mention how it works in principle. So this is how instrumentation happens. So normally, when you load an application into a runtime environment, you start with some code on your disk, and it loads into memory and starts executing. Well, with instrumentation, you add an agent to your runtime environment that hooks that loading process and modifies that code as it loads, adding in sensors, like little callbacks that allow you to gather data directly from the running application. So this is really a powerful technique. It allows you to see what's going on inside the application as it runs. So you can use this to do really accurate data flow analysis. You can interrogate the application to get how things are configured, and so on. So then as that code runs, you get feedback, and you can analyze the events that happen during the running application and identify vulnerabilities, ways of improving security, and so on. So that's the concept behind instrumentation. And ultimately, you get this, your code is enhanced with security now. This is the kind of information that instrumentation can give you access to. So instrumentation can see the code because it's running there. It can do binary static analysis. Instrumentation can see all the HTTP traffic in and out. So it can do things that are a little bit like a DAST scanner by monitoring that stuff. It can also see the actual back-end connections. So if you're looking for SQL injection, it's really helpful to be able to see the actual SQL query as it went to the database. Right? That's the kind of insight that you can get with with instrumentation, you can see all the libraries and frameworks and how they're used. You can see the configuration data. And this is really important, is this runtime data flow is absolutely critical. Imagine, if any of you are pen testers, imagine how awesome it would be to see exactly the path that whatever data you send into an application takes through the code, where it hits, what interfaces it goes to, and how it works. That's what instrumentation can provide. So some advantages to this: you don't have to intercept the traffic on the wire. And this is incredibly important for APIs because, as we're going to see in a second, that's one of the biggest challenges, is just getting access to the data. Instrumentation sees the data after it's already come off the wire, as it's flowing through the code. So you can see it and analyze it there. So let's talk about some of the complexity factors that make APIs difficult to analyze automatically. And again, you can do these things by hand, but I'm looking for automated approaches here that'll scale. So the first thing is frameworks. This is an example of a Spring REST interface. And all someone really had to do here was write a little controller that maps requests to this and say, hey, this is a REST controller. So we've got these two annotations. And this, which means, hey, take the value from the URL, the name value, and it's got a default value of world, and use that to generate a new greeting, and then return it, that's a really powerful little controller, but it ends up working. So now you send this URL in with the name equals user, it comes back with a JSON payload that says, hello, user, right? Really powerful. But in order to understand if that's got vulnerabilities in it, I need to understand what all those annotations mean. And unfortunately, there's a ton of frameworks out there. So I went I spent maybe 10 minutes and came up with a list of, these are just Java frameworks for building web services and other kinds of services. So this is really hard for tools to keep up with, right? They got to understand all that stuff if they want to find vulnerabilities. So another complexity here is the protocol level. And so I'm just trying to work up the stack here a little bit. So the first thing is that protocol layer could be anything for a service, right? So if the developer creates a WebSocket to the browser, he can send whatever he wants over that connection, right? He could send any kind of data. He could wrap it in other protocols like SOAP or XMPP or whatever to send data over that connection. And it could be a custom protocol. My son wrote a game. He's a high school student. He wrote a game on JMonkey. It's a 3D graphics engine, but he wanted it to be multiplayer. So he crafted up his own little protocol, sending UDP messages back around my home network. And he didn't know how to use XML or JSON or anything, so he just sent comma-separated values over in a UDP packet. And then when the data got there, he parsed it, right? So he's just writing his own little protocol to handle this level of stuff. And developers will do that because the power that they have now. With HTTP, it's pretty constrained. You got name-value pairs to send data back and forth in. Now we've got all these complex structures to send data back and forth in. So intercepting these protocols is sort of arbitrarily hard. Right? If people stick to standards like REST over HTTP or something, then you can intercept that traffic with a standard tool and do stuff with it. But if they're doing crazy stuff, then it's going to be arbitrarily difficult to intercept that traffic. If there's SSL involved, it gets even harder. I've seen a lot of work done in this on testing mobile clients. So not always easy to set up a proxy in a mobile client connection, particularly if SSL is involved. So you can try a reverse proxy. You might have to modify the trust store. If that doesn't work, you might have to actually reverse the code and recompile it. There's to use a forward proxy. You can also use this tool called iOS kill switch, which is pretty cool, which sort of disables certificate validation in iOS. A bunch of different things that you might have to do. You might spend your whole week when you're supposed to be testing, just getting proxy working so that you can actually do the test. So I think this problem's going to get worse. I think we've been in a golden age of pen testing for the last 10 or 15 years because it's been really easy to intercept traffic and modify it, but it's about to get way, way harder. So then the next level up is, imagine you got the protocol level handled. Now the data level. How do we parse whatever we get? Well, parsers are really powerful. And the more complicated they are, the more features they have, the more it's possible to abuse them. So I'm going to talk about a couple of different parsers here and things that you can do to give you sort of a sense. But remember, this is data that's coming from an untrusted source. You're bringing it into your application, and you're just handing it off to some parser to do whatever it's going to do. So let's look at URLs. And there's this great paper called Resting on Your Laurels from Dennis Cruz, who's another longtime OWASP guy. But I encourage you to read that. Some of these are described more fully in there. But even just URLs that you'd use to invoke a REST service can be really powerful. There's a lot that can go on inside a URL. So sometimes you can pass in credentials inside the URL. Sometimes anybody know HTTP parameter pollution? Basically, you're overloading parameters in the URL. So you give like 3 different values for the foo parameter. And then what happens to them inside the service is not well defined. It's different on different platforms. Sometimes they get concatenated together, and they might even concatenate together to form an attack. So if there's some security filter that's trying to look at the data, it might see 3 individual pieces, none of which looks like an attack, but HTTP parameter pollution pulls them together and turns it into an attack when it gets into the parser. I didn't know about this one, this faking the method. This is kind of cool. Some systems out there allow you to add a underscore method parameter to your URL. So just a simple question mark underscore method equals post. And you can turn a get into a post in terms of how the processing happens on the server. So I thought that was really an interesting attack. That'll bypass certain kinds of security defenses that you might have in place. And every one of these back-end systems that has a REST API has its own URL format. So some of them are really powerful. Like NoSQL has a great way to just explore the schema of a database just by sending in URLs and browsing around. So there's a huge variety of URLs that services can take. And this all makes it difficult to test automatically, right? Again, I'm not saying you can't go test this manually. You guys are experts. But we need to have tools that can do this. And so I'm suspicious that they're not going to be able to handle this, this 1,000 points of light kind of variations in these URLs. This is a GWT request. That's the Google Web Toolkit. Just another example of a complex data format that is now difficult to test with compared to something like HTTP. You're used to using, Zap or Burp or something. You can't do it with this. Turns out that this is not just a straightforward data structure. These fields refer to each other. So if you change something up here, you have to change some other stuff down here to maintain it as a valid data format. So really difficult to test this. There are some plugins now that you can get for GWT, but the problem is we don't have those plugins for every one of these protocols, right? People are dreaming up all kinds of data formats, and we don't have the tools to go automate them, at least in terms of intercepting them on the wire. XML has a bunch of interesting properties that not all developers know about. So you've probably seen some of these attacks. The billion laughs attack, where you create one entity that makes it 2, that makes it 4, and 8, and so on, to blow up the parser. XXE, I think, is really important. I'm going to campaign for this to get into the next version of the OS Top 10, because it's pretty widespread and becoming more prevalent. But if you search for XXE vulnerabilities in web service frameworks, you'll see almost every single one of them has a security finding that says, hey, we got XXE. Because everyone builds it this way the first time. Server-side request forgery, interesting attack. This is where you send in an XML document with a doc type in it, and in that doc type, you define an external entity with a URL. And so then when the parser parses that XML document, it actually reaches out. It sends an HTTP request out on the back end. This is on your internal network. It sends a URL out to some other application that you have internally. So people can use your XML parser to scan your network and figure out what hosts are running where and access URLs, and even invoke other APIs. If you've got other REST APIs that you can invoke with a URL, you can do it with SSRF. So this is also a big deal. And this last one is pretty neat. This is another one that Dennis Cruz found, is an XML decoder. This is the standard XML decoder class in Java. And it actually, if you send in a carefully crafted chunk of XML that says class name, runtime, method name, exec, and then a bunch of parameters, all in XML, this XML parser will parse that XML, pull out the method, and then use reflection to invoke it. So it's like a great way to get some code running on the server just by hitting an XML, sending an XML document to a web service. So parsers are powerful, and developers use them without really thinking about all the ways that they might be abused. Oh yeah, and then the last problem, this is interesting, is you actually don't know what parser is actually going to be used, like the implementation of that parser. So developers can write their code to a certain API, like JAX-P, for instance, is the Java API for XML processing. The developers just write their code to JAX-P, and then they can deploy it wherever they want, and it just works. But it turns out they don't know what XML parser is actually going to be used under the hood. So there's actually a sort of a hierarchy, a search strategy for finding what parser to use. It says, first you look at a system property to see if that's defined. Then it checks this properties file, if that's there in Java home somewhere. Then it uses this meta-inf thing. And then this last thing is it's got some fallback default platform implementation, which I'm guessing 9 times out of 10 is where this thing ends up, because nobody's probably specified it. So this is a real problem if you're trying to do code analysis and you don't know what code is running until runtime. Your static analysis tool isn't going to be able to analyze this. OK, so that's the parser level. Next level, auto binding. A lot of the frameworks do this now, is you don't have to call request.getParameter anymore, or request.getHeader or getCookie or anything. All that stuff is abstracted down into the framework somewhere. So this makes it really difficult for tools, right? They can't do the data flow analysis if they can't see the sources and the sinks. Well, now the sources and sinks are buried in the frameworks. So here's an example of some data coming in from a user. Request comes in. The framework grabs the request, parses the XML, automatically takes the data out of the XML, and maps it into a bean. So here you can see the date property and the SSN property are being set in this bean. This is interesting. This is a private member of this. We've got this customer class here, and it's got a private member called account balance that the developer probably didn't think was going to get mapped because there's no field over here called account balance. But what we found is in a lot of auto binding systems, you can just you can fake that field in here as an attacker, and the web data binder doesn't care. It does reflection on that field and says, oh, there's an account balance field. I'm just going to overwrite it with the value. And so then all of a sudden the attacker is now setting this private field which he wasn't supposed to have access to. So auto binding is a big deal because it makes it harder for automated security analysis tools to understand what the code is doing. It used to be pretty easy. You could just look for the call to where we got the untrusted data out of the HTTP request directly. But now it's going through layers and layers of stuff, which means we have to understand all these frameworks if we want to understand how to find these vulnerabilities. So real quick, what do you think happens if you take a bunch of source code and feed it into a static analysis tool, that, so this web service code with complicated parsers and complicated data binding and so on, what do you think the static analysis tool does? It runs for 5 hours, that's right. And then it generates a report, right? It's going to spit out something. It's going to say, hey, you use system out print line here and there. But is it going to tell you that it missed stuff? This is the danger, right? People have a false sense of security in these tools because they don't know what they're missing. So I really want you to think about this, because people, there's companies that are just, they're taking all their code, they're running it through their process, and they're running it through static analysis, but they don't realize that it's got these major gaps, particularly where APIs are involved. Okay, so I want to go through 6 differences with, from traditional web applications to web services. So the first thing is communications, and we'll go sort of right on down. I'll give some examples of this. So we talked a little bit about custom communications. I think this makes it easier for static and IaaS tools to analyze services because they have access to the code. They don't have to break into these custom protocols and reverse engineer them. So this is, there's some advantages here. Try to stick to standards when you're looking at building web services, because that'll make it much easier to intercept and test. Second difference is specifications. We never had a spec for a web application, right? You just build a web application with a bunch of UI, and developers are adding fields and form fields and processing and so on. And there's never really a spec level. But APIs often have a spec, right? And it started way back with like RMI and Corba and stuff like that. But now, for web services, you'll see WSDLs and you might see XML might have a DTD associated with it. Anybody using Swagger? A couple people. This is really cool stuff. I'm going to show you an example on the next page. But the idea of having a spec for an API should make it easier for tools, right? This is actually something that's good. I'm not all bad news. This is something that's good for tools, because now we could, in theory, we could give our tool the spec for the API, and now it can automatically test it, right? So there's 2 ways that people use these specs that I've seen. One is you write the spec first, and you generate the API from the spec, which that sounds good, right? The other way is you actually build the API first, and then you're like, oh crap, we need some documentation. So you reverse engineer the spec from the API, and then you publish that, right? Good news is it doesn't really matter, because from a security perspective, you can use that interface to test the API and verify that it's doing the right stuff. And actually, if you spend time verifying, even if you just verified the spec, as long as you have confidence that the spec is actually has good traceability to the actual implementation, then you can get some assurance simply by analyzing the spec. So we need better tools there. And if you're looking to make a name for yourself, I think building some tools to analyze the security of, say, a Swagger spec. And I've got an example of one of those here. This is a little chunk of Swagger. But build a tool that analyzes this and gives people security guidance on how to beef up the security of their spec. That would be really cool. And we need those tools for all different kinds of these specs. So Swagger's kind of neat because it actually does have some security stuff in it, right? You can specify the HTTP method. You can specify authentication and authorization stuff, and even things about the different parameters to the API. Now, what I have seen, and this is over a long history of looking at web services, I see that most of these specs are garbage. I've seen a lot of XSDs, the XML schemas, where every field is defined as XSD string. It doesn't really stop any attacks if you can allow any string into that API. So I want you to be careful about trusting these schemas. And you can't just say, oh, well, it went through XSD validation, so we can trust it. Because they really are almost all that way. Next thing is control flow. So control flow analysis is pretty important. See what code executes in what order. And the problem with APIs is that it's really difficult to tell what code is actually running. There's lots of libraries involved. A lot of this is assembled at runtime, so you can't really count on what's there at compile time. And you'll see a lot of inversion of control and reflection and dynamically loaded code, which causes real problems for some kinds of tools. Now, this is one where DAST tools don't care. They're just scanning the external part of the API, and whatever's running in production, that's what they're going to test. Same thing with IAST. It's just going to see just what code is running in production and analyze that. Data flow. We've talked about this a little bit. I mentioned that the sources and sinks and propagators are now sort of deep in these libraries. This is just complexity for different kinds of tools. I think IAST has a good shot on this one. I think of the different tools, data flow analysis in IAST is really accurate because it's actually watching the actual data flow through the application. So it's not like, like a static tool has to build a model of the application and then mathematically try to prove what data is flowing where. This is just actually watching the actual data flow. Authentication and authorization is almost always custom in applications. I wish there were more standards around this, but this makes it really hard to test them. So no matter what technology you're using, you're going to probably have to build some custom rules to check your authentication and authorization rules. And then the last one is called futures and promises. Anybody familiar with futures and promises? A couple developers in here? OK, so this is a relatively new programming construct. It's new to Java and other languages. But the idea is you can create a task to execute and then get the results from that some point in the future. You might think of it as a promise to execute something. But it's a concurrency scheme. So in this diagram, you can see the old way we would have had to build one of these services is we would say, hey, you guys probably can't read that. It says, go get the customer details, and that takes 150 milliseconds. Then get a list of recommended destinations. That's 200 milliseconds. Then iterate through each of those destinations and get a quote. And then iterate through each one of those and get the weather for each one of those. And when you add it all up, it's like 5 seconds worth of work. But with futures, you can actually thread that. So you do this one step where you get a list of the destinations. That still takes 250 milliseconds. But then you can spin up all these futures to go run these in parallel. And so you end up, the whole thing just takes as long as the longest one. So you cut your time down to 730 milliseconds overall. And the only reason I mention this is because it really makes things difficult for automated tools if you've got all this concurrent code running all the time. So your static analysis tool now doesn't have to just build this one linear model. Now it has to build a model with all these concurrent things executing at the same time. So it makes it much, much more difficult to analyze. And a bunch of the new frameworks do this automatically, like Netty and Play and Grizzly. Some of the most high-performance API environments are really doubling down on this strategy. OK, so that's 6 differences. What I want to get to is, OK, so great, it's complicated. What do I do to take my expected security model? This is like, you might call this security requirements or policy, or if you're really good, you call it test cases. And how do we match up different tools to the different things in my expected security model, right? How do we choose which thing we're going to use to verify each one of these things? And again, this is how you should think about security, is don't think about, did I run tool X on that application? Think about, how much coverage do I have over my expected security model, the defenses that I expect this application to have? Because this is what you're being measured against. So there's not a great way to choose this, because nobody knows what any of these tools actually do, right? There's some rule set in there that says, well, I cover SQL injection. Well, what does that really mean? Do they cover all the different variants of SQL injection? Do they handle all the different types of data flow that could lead to a SQL injection? They don't advertise. It's certainly not in their marketing material. They just say, we do the OWASP top 10. So OWASP comes to the rescue. earlier, like very early this year, some guys started a new project called the OS Benchmark Project, and they're building an extensive test suite to test application security tools to see what they actually do and what they don't do. And what's, as I've watched this project evolve, it occurs to me that this is the only way you're ever going to know what these tools actually do well. You've got to test them. And so this is actually really good science. It's all on GitHub, so you can pull it down and look at all the test cases. It's totally reproducible. Anybody can run it. And let me show you a little bit how this works. So they built over 21,000 test cases, and for each of these categories. And in each one, they've got a bunch of true positives and a bunch of false positives, because they're really trying to test exactly what the tools are good at. And it's across these 11 categories. When I look at these test cases, it's the easy stuff. There's nothing really complicated here. This is what they've built so far is primarily standard servlets with standard kinds of SQL injection flaws and XSS flaws and all these different kinds of flaws. Nothing surprising or complicated here. Not a lot of frameworks and stuff. I'll talk about that in just a second. But this is the kind of stuff that tools should ace. So here's what you can do if you want to try it. You can clone the GitHub repository. If you've got access to one of these static analysis tools, you can just point it at the directory and run the static analysis tool. If you've got a DAST tool, you can actually run the test suite as an application and point your scanner at it and let it scan it. And if you've got an IaaS tool, you can use that along with the running application as well. And then you take the report that comes out of your tool and you feed it into this other thing that they built called the Scorecard Generator, which takes the expected results for all the test cases and parses all these reports. So you can feed in a Fortify report or a Veracode report or whatever. You feed it in, it parses it, it does the math, and it creates these cool scorecards that tell you exactly what the tools are good at and what they're not good at. So here's a part of the output. There's also like a big table full of data that shows you all the numerics. But they also produce this chart, which I like, and they report in this format. They say, here's the false positive rate for the tool, and here's the true positive rate for the tool. So a tool down in this corner is not reporting anything, right? It's not finding the true positives. It's not finding the false positives. So that's a tool that's obviously terrible. What's more interesting is up in this corner, this is a tool that reports all the true positives. Great, right? But it's also reporting all the false positives. So if you think about it, you can write a tool like that in a couple hours, right? All you have to do is report every vulnerability on every line of code. So there's no value there to tools that do this. It's just noise. And so they call this line, the project calls this line the random guess line. And if you've got a tool that's in here, it's basically just flipping a coin. And hey, should I report this vulnerability for this test case or not? You wouldn't expect anything down in this corner because that would be sort of worse than guessing. And you should just do the opposite of what that tool says. So I want to make this point here. This is really important, is that every false alarm costs you one true vulnerability. It costs you the ability to protect your organization against one true vulnerability. Because all of your organizations are resource constrained. You don't have enough people to go do all this work. So if you spend the time to check out, when you get the vulnerability, you don't know if it's a false alarm or not, right? So when you get it, you got to spend most of the time going and investigating it. Is it real? How do I fix it? Let's check it out. And then when you finally get there and you realize, oh, it's not a vulnerability, then you just wasted all that time. So that's an opportunity cost. It prevents you from being able to check out a real vulnerability and actually make something more secure. So false alarms are really, really important. Obviously, you want tools that are up in this upper left-hand corner. So the results are fascinating. I strongly encourage you to go look at the project. OWASP won't publish the results unless commercial vendors say it's OK to publish the results. So you're going to have to, there's a few vendors like my company that have published their results. Fortify also sort of published their results. But you should run this with your tool and check out how it does. There's no other way for you to get the results out of this, unfortunately. It would be great if somebody just said, oh, we're going to pull it all together and make a master list out of it. But the cool thing is, some tools are really amazing at certain things. They get perfect score on things like insecure cookies or weak encryption algorithm. Other tools have amazing, inexplicable weaknesses. So there's one major static analysis tool that doesn't report XPath injection or LDAP injection. They just don't do it. And there's no explanation for it. And this is interesting. In almost every category, the best SAST tool, DAST tool, and IaaS tool is different. Okay, so there's not one tool that's just better across the board on these things in these categories. You got to look to see what these tools are good at. The project is working. It's already, a number of companies have come out in support of the project, and a bunch of tools have already improved their tools because of the benchmark. So this is how OWASP improves the world. We build this benchmark to measure stuff so that then people build tools that actually work. So what we're doing, Contrast is donating 1,100 some new test cases to test APIs. So we built a test suite that's got smaller numbers of test cases, but we'll build this out as we go forward. But these are API test cases, REST APIs and web service APIs and things like that. So it's 132,000 lines of code, and the results are fascinating. So I ran, I'm not going to tell you the tools, but I ran 2 of the major static analysis tools against our test cases. And here's what the test cases look like, by the way. This is a simple example that does, what is this, a command injection, okay? So you can see here, for a tool to find this, they'd have to know that, hey, look, this is a REST controller, that we've got a request mapping for this URL, that this is the request body is being parsed into a person, and then it has to do the propagation here to pull the get name into this param, and then trace that down and see that, hey, this is being combined into the runtime exec, okay? So that's how you do it manually. But if you're a tool, that's pretty tricky because you got to know all these annotations. So the first tool didn't do great. You can see they did OK against weak random numbers and weak encryption algorithms. Those problems are like one line of code kinds of problems. So it's not surprising that static analysis tools did fairly well against that. But you look down here, all the rest of them, they're at 0 or very close to 0. So they didn't find a lot of these vulnerabilities. Let's see, what's A is command injection. So they did better at command injection in terms of finding true positives, but they also flagged just as many false positives, okay? So they're on that random guess line. So that's interesting. They reported a total of 3,000 vulnerabilities. Now the next tool, and this is where it gets fascinating, right? So I would have expected this, because I didn't think, my thesis going into this research was that these tools wouldn't do very well here. But the next one is fascinating. So this is another very popular static analysis tool, and you can see the results are almost exactly the opposite. So the first thing you'll notice is that they're way up in this corner. They're not down here. They're way up in this corner, so they're reporting everything, whereas the other tool was reporting nothing. Interesting strategy. So they've got, this is command injection and LDAP injection and SQL injection. All that stuff is up here. You can see they did well on insecure cookies and weak hash algorithm. But they didn't do well on weak encryption algorithm, which is just kind of weird. And then down here, they didn't report weak random numbers at all, which is strange. The worst thing about this, though, is this number right here. Did anybody see this? So remember, this is 130,000 lines of code. They reported 560,000 vulnerabilities. And the reason is static analysis tools look at all the paths to get to a particular vulnerability, and for some reason, it just threw up on this. It must have thought there was like a zillion paths to get to these vulnerabilities. So fascinating results. And this is why I say, if you want to use tools, you've got to know what they're good at and what they're not good at, because it's not intuitive. And stuff that I thought would have been a no-brainer, tools don't do it. So we need help. OWASP needs help. This is important research. This is probably, in my mind, one of the most important things that OWASP can possibly do in terms of improving software security for everybody, because it's driving a force multiplier, right? If we can affect the tools and make the tools better, we affect zillions of people in a way that the OWASP top 10 never can. So we need better test cases, more test cases to test all different aspects of these tools. They're not hard to write. If you're interested in some obscure vulnerability, write some test cases and contribute them to the benchmark project, because then they'll get picked up and you'll make a difference. The other thing is, I think we need better guidance on APIs to tell people how to build safe APIs, how to test APIs, and how to use APIs securely. And there's an awful lot of work left to be done around this. I firmly believe that the API economy is the future here. So this is really important work in a way that you can make a difference. And don't think it's too late, because I wrote the OWASP Top 10 in 2002. And at the time I wrote it, I thought it was too late. And it hasn't changed in how many 14 years, whatever that is. So you can make a big difference here, because we've got a long future ahead of us. The test suite is randomly generated from a bunch of components. So like every 6 months or so, they're going to just re-randomize and put out a new version of the suite with more test cases and more stuff in it. So that should help. The other thing is, I think there are things that you could do to the test suite to randomize it yourself a little bit, so that tool providers can't just say, oh, well, I know what the expected results are. Like you could sort of shuffle the expected results and shuffle the test cases, so that it's like giving every person a different version of the test when you take a test in class to prevent cheating. Good question.
All right, that's super technical.
Thanks.